tell me whether you can see my... Can you see my screen?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Hello? Yes? Yes? Everyone has joined. You can also join. Use that link and join. Okay, class has already started. Just use the WhatsApp link and join. Then नहीं सभी ने ज्वाइन किया, तुम्हारा भी हो जाएगा, नहीं तो तुम्हारा कोई नेटवर्क इशू है, सभी ने ज्वाइन किया. Just click on that link. Yeah. Yeah. You join. Okay. Okay. So, so this is our second class. I hope you got your, I sent the note of the first class. I uploaded the PPT class and I also sent the note of the first class last Tuesday. I hope all of you got that. I sent it in LMS. So please check for the note, and the PPT class is also uploaded in LMS. And of course, the previous week's class is there in my YouTube channel also. So you can always go back and if you want to recap something. All right. So today we'll start directly with vector products. I introduced vectors to you in my last class, and we talked about how vectors can be represented in the geometrical form and in the component form. And I told you how the component form is easier to handle because although the geometrical form lets us visualize the vector, but using the component form, it is easier to do mathematical, numericals and mathematical problems, because we just have to handle the coefficients of the unit vectors. And then we talked about linear dependence and independence. Okay, so today we'll directly start off with vector multiplication, okay, product of two vectors. Now, vector multiplication can be of two types, all right? First type is scalar or dot product. So from the name itself, you can understand that the result of this kind of multiplication is a scalar, all right? And it is also called, it is more popularly known as the dot product. So by definition, suppose you have a vector A like this and another vector B like this. Wherever the vectors are, you know from our previous discussion that we can always parallelly displace them and make them oriented in this manner, both touching at the tail. So suppose the angle between these two vectors is theta, then by definition, this is the dot product, okay? Vector A, you write a dot in between, vector B is equal to C, where C is a scalar, okay? So how do we do the calculation? This is the definition. How do we do the calculation? So the value of C is this. Modulus of A is a scalar number, modulus of B is a scalar number. So product of those two, the modulus of A and B, and with it, the product of the cosine of the angle theta between the two vectors, okay? So this is the definition of the dot product, all right? So obviously, from this definition, it follows that first of all, if the angle theta between the two vectors is 0, then the product will be just the product of the modulus of the two vectors. I'm sorry about this arrow. It has been printed in the opposite direction. It doesn't mean anything. It should be the normal arrow. So if theta is 0, we know that cos theta is 1. so that A dot B equal to just the product of the modulus of A and B. On the other hand, if theta is 90 degree, that is if the two vectors are perpendicular to each other, then the dot product is 0 because cos 90 is 0. Okay, so if you find that the dot product of two vectors is 0, then at once you can say that the two vectors are perpendicular to each other. On the other hand, if you see that the dot product of two vectors is just the result of the multiplication of the modulus of the two vectors, then you can say that the two vectors have 0 angle between them, which means you can see that if this angle theta is 0, it means that the two vectors are along the same direction, that is they are parallel to each other. All right. Okay. Now from this definition, we can write that if one of the vectors is A and the other vector in place of B, if I write I cap is the unit vector along the x direction, then we know from our previous classes definition that the angle that a vector makes with the coordinate axis are defined as alpha, beta and gamma. Remember the direction cosines we defined in our last class. So A dot I will be modulus of A into modulus of I into cos of alpha, because alpha is the angle that A makes with the x-axis, that is with I. But we know that the value of I mod I is 1. I cap is the unit vector, so its magnitude is 1, so that we are left with A cos alpha, which is nothing but Ax. If you remember, we defined the components of a vector in this manner, that A cos alpha is Ax. Similarly, A dot j will give you A cos beta, that is Ay, and A dot k will give you A cos gamma, that is Az, which means that the projection of a vector onto a coordinate axis will give the Cartesian component along that axis. Okay, so you get another meaning of the components of the vector, that is the components of a given vector along the three Cartesian axes are nothing but the projection of the vector along that axis. Okay, so this is another way of looking at the components using the concept of dot product. All right, now we can see that A dot B, suppose I keep A like that and I write B in the component form. Okay, so A dot, I write expand B in the component form as Bx x cap plus By y cap plus Bz z cap. Okay, so Bx, By and Bz are scalars, so they can come outside. So I can write this as Bx A dot x cap plus By A dot y cap plus Bz A dot z cap. X cap, y cap, z cap is the same as I cap, j cap, k cap. All right. So you can see that A dot x cap is nothing but Ax, A dot y cap is nothing but Ay, and A dot z cap is nothing but Az. So I can write this expression as Bxax plus Byay plus Bzaz. But Ax, Bx, Ay, By, Az, Bz, these are all scalars. So Bxax is the same as Ax, Bx, right? So you can
ম্যাম শোনা যাচ্ছে না।
হ্যাঁ ম্যাম শোনা যাচ্ছে না ম্যাম।
We are not listening, ma'am.
ম্যাম আপনাকে কে মিউট করে দিয়েছে?
আমাকে যদি কেউ মিউট করে দেয়, আমি তো বললাম যে আমি যখন প্রেজেন্ট করছি তখন তো আমার পক্ষে আমি তো এই স্ক্রিনটা দেখতে পাচ্ছি না, আমি তো আমার পাওয়ার পয়েন্টটা দেখতে পাচ্ছি, তাহলে তার মধ্যে আমাকে তোমাদের মধ্যে যদি কেউ মিউট করে দেয় তাহলে তো খুব মুশকিল না? এটা তো করাটা একটু মানে ভুল করেও এটা করাটা ঠিক নয়। তোমরা কেউ বাচ্চা ছেলে মেয়ে নাও, যে প্রেজেন্ট করছে তাকেই মিউট করে দিলে তো বাকিদের অসুবিধে। whoever is doing this muting me, please if you are not interested then leave the meeting, but don't create a nuisance inside the meeting, please. This is my request now. Next time I will remove you myself. কোথার থেকে শুনতে পাওনি তোমরা? Can someone tell me from where have you not been able to listen to me? কোথা থেকে শুনতে পাওনি সেখান থেকে আমি আবার রিপিট করব। কোন কোন জায়গাটার থেকে শুনতে পাওনি? Can someone tell me কোন জায়গাটার থেকে শোনা যায়নি?
Ma'am, BXAX.
Okay. Once if I stop presenting, then I have to go back to the entire slide. I mean, this is a lot of waste of time. None of us, neither do I have so much time, nor do you have so much time. We have 45 to 50 minutes in a class, and I have to cover a lot of the syllabus. So please don't create a disturbance. Okay. So as I was telling you that A dot B, for B you can write it in the component form as bx x cap plus by y cap plus bz z cap. So since bx, by and bz are scalars, you can take it out and you can write this in this form. But we know that A dot x cap is ax, x component of A dot y cap is ay, y component of A, and A dot z cap is az, z component of A. So in place of A dot x cap, A dot y cap and A dot z cap, we can write ax, ay and az. So this expression becomes bxax plus byay plus bzaz. So we can write that in component notation, the dot product is the sum of the product of the individual components, and the dot product is commutative. That is, A dot B is equal to B dot A. All right. So you have to remember two ways of finding out the dot product. One is this formula, A dot B equal to magnitude of A into magnitude of B into cosine of the angle between them. And the other formula is sum of the individual component, sum of the product of the individual components along the three directions. Okay. So these are the two formulae of dot product which you have to remember. Now, how do we physically interpret the dot product? See, since the unit vectors, if you take the dot product of the unit vectors with themselves, then each will give you 1, because we know that if theta is 0, cos theta is 1, so the dot product becomes 1. On the other hand, since x dot y cap, x dot z cap, y dot z cap are each 0, because the axes are mutually perpendicular to each other. Okay. Example of dot product, you all have faced this earlier. Work done. Work done is the dot product of force and displacement. All right. So if direction of force and displacement of the body are same, we know that work done is maximum. F dot S will become just the product of the magnitudes of F and S, because cos theta becomes 1. So if the body is displaced in the same direction in which the force is acting on it, then work done is maximum. On the other hand, if direction of force and displacement are perpendicular, then work done is 0. So no matter how much force you give, if the body is displaced at 90 degrees to the direction of force, then work done is 0, and you know that such kinds of work are known as no work forces. The forces that do not produce any work because the displacement is perpendicular to the direction of the force, they are known as no work forces. You have already done this in your +2 mechanics and physics. Okay. Example, very important example, which you might not have encountered before, is the normal to a plane. Okay, how do we find the normal to a given plane? Okay, let's consider a vector r, which is x cap plus y cap, which means that the vector r is a vector in the xy plane. Any vector in the xy plane can be written in this manner, x cap plus y cap. So this is what I'm talking about. This is the xy plane, okay, and this is the vector r, x cap plus y cap. Now, if there is a vector n cap, which is a unit vector, and if for whatever value of r we have, whatever form of expression of r we have, which means that whatever the values of x and y, so depending on the values of x and y, r will be oriented in different manners in the xy plane, right? So if there is a unit vector n cap such that n cap dot r is 0 for all expressions of r in the xy plane, then we say that n cap is perpendicular to the entire xy plane. That is, n cap is a normal to the entire xy plane. So this is then the direction of n cap. This is how we define the normal to a plane. When we can say a particular unit vector is a unit normal to a given plane, if the dot product of that particular unit vector with any vector r lying in the xy plane is 0, then we can say that n cap is a normal to the entire plane. All right. So we get two practical instances where we use dot product. Okay, one is in work done and the other is geometrical, that is finding out the normal to a given plane. All right, I am giving these examples because you might get small, short numericals from these kinds of examples. So that is dot product. Next we move over to vector or cross product. I told you multiplication of vector can be of two types. One is dot product and the other is cross product. So we discussed dot product. Next we will discuss cross product. As you can see from the name itself, that in dot product we had seen that the result was a scalar. In cross product we will see that the result is a vector. So by definition, this is how we define cross product. Okay, A cross B equal to C, and as you can see that the result here C is a vector. So it is a vector which is assigned a direction perpendicular to the plane of A and B. C is a vector which is assigned a direction perpendicular to the plane of both A and B. So if you take the cross product, then you get a vector, and that vector has a direction which is perpendicular to both the given vectors. That is the plane containing A and B. You can pass only one plane through two vectors. So the cross product is a vector perpendicular to that plane. A, B and C therefore will form a right-handed system. Right-handed system means A cross B will give you C, B cross C will give you A, C cross A will give you B. That is what I mean by a right-handed system. I'll repeat once again. A cross B will give you C, B cross C will give you A, and C cross A will give you B. That is a right-handed system. On the other hand, B cross A will give you minus C. C cross B will give you minus A, and C cross A will give you minus B. Okay, so if you change the position of the vectors in a cross product, then you get the negative of the earlier result. So we saw that dot product was commutative. A dot B is equal to B dot A, but cross product is not commutative. That is, A cross B is not equal to B cross A. Okay, just please remember this for future reference. So if we have a vector A like this and a vector B like this, and as earlier the angle between the vectors is theta, then by definition A cross B, the magnitude, is given by product of the magnitude of A and B and sine of the angle theta between them. So dot product was cosine of the angle, cross product is sine of the angle. So as a result, x cross x, y cross y, z cross z will all be 0, because if theta is 0, then the value of the cross product becomes 0. In other words, if two vectors are parallel to each other, the cross product becomes 0. On the other hand, x cross y will give you z, y cross z will give you x, z cross x will give you y. Again, because it forms a right-handed system, and we know that x, y and z are mutually orthogonal to each other. So crossing any two will give you the third one, but in this order. If you go in the reverse order, you will get the negative. Just as this, y cross x is minus z, z cross y is minus x, and x cross z is minus y. All right. In component notation, the cross product A cross B is this. So you have to find the determinant, where the first row is I cap, j cap, k cap. The second row is the components of the first vector A, and the third row is the components of the second vector B. So once you know the two vectors, you can write down these components of the determinant, and you can find out the vector C, which is the cross product. All right. So this is how we get the cross product of a vector. Two formulae again, either A, B sine theta or this determinant. From this determinant, you get the resultant vector in the component form, and from this formula, you get the magnitude. So these are the two formulae that you have to use if you are asked to find the cross product between any two vectors. Just remember that for dot product, the result is a scalar. For cross product, the result is a vector. What is the geometrical interpretation of a cross product? How will you geometrically interpret the cross product of two vectors? This is how we geometrically interpret the cross product of two vectors. So we have the vector A along the x-axis, and this is the orientation of the vector B. So you can draw the parallelogram PQRS, where PQ is formed by the vector B and PS is formed by the vector A. So you can see that theta is the angle between A and B. So you can see from this figure that B sine theta is the height of the parallelogram. Correct? B sine theta gives you the height of the parallelogram. Therefore, when you take the cross product A cross B, you get AB sine theta, but magnitude of A is the base. So basically this is height into base of a parallelogram, which means that you get the area of the parallelogram. So when you are taking cross product of two vectors, the magnitude that you get is the area of the parallelogram, the sides of which are formed by the given vectors. All right. And the direction of the vector is, as I told you, earlier in the definition of cross product that the direction of the vector is normal to the plane of the parallelogram. So the magnitude is the area of the parallelogram and the direction will be normal. So if this is the plane, if the screen is the plane, then the magnitude of the resultant vector of the cross product of A and B will be coming out from this plane, okay, outward, perpendicularly outwards towards you. If you are looking at your mobile screen or your laptop screen, then the direction of this vector is coming perpendicularly outward from the screen towards you. I hope all of you have understood and visualized. Okay, this is why area with its space orientation may be treated as a vector. When we do vector differentiation and vector integration, you will see that I will assign area as a vector. So long you have assigned only lengths as vectors, right? Linear displacements were associated with vectors. Now, from this concept, you will see that a given area can be treated as a vector because a given area is nothing but the cross product of two vectors, and the cross product is a vector, the direction of which is perpendicular to the plane containing the two vectors. So any given area in space, if its space orientation is given, then it can be treated as a vector. Please remember this because we will need this reference in our future classes on vector differentiation and vector integration. Okay. Next, we will do triple product. In dot product and cross product, we had multiplied only two vectors, A and B, either giving you a scalar or a vector. The third kind of product is vector triple product. Now, vector triple product can be of two kinds. One is scalar, and this is the formula: A dot B cross C, or B dot C cross A, or C dot A cross B, but all of them give you the same value. A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. So all these three give the same result, and we will see geometrically what it means. So suppose this is my coordinate axis x, y, z, and suppose we have these three vectors A, B, and C. They are randomly oriented in space, okay? They can be of any direction. I have chosen just randomly any three directions of A, B, and C. Now, see, if you look at the first expression, A dot B cross C, B cross C is BC sine theta, right? And BC sine theta is nothing but a parallelogram area. As we had seen in, if I take you back to this slide, the cross product of any two vectors is the parallelogram, correct? So, if you have taken these three vectors, and if you are leaving aside A for the time being, if you're taking just B cross C, then B cross C will be the parallelogram of which B and C form the sides. So, this is B cross C, correct? The parallelogram. And what will be the direction? The magnitude is given by this, the parallelogram, and what will be the direction? Direction is normal to the plane containing B and C. So direction will be something like this: B cross C, normal to the plane containing B and C. So when you are taking the dot product of A with the normal to this parallelogram formed by B and C, it means that you are multiplying the base area with the projection of the vector A onto the normal. This is the direction. So A dot B cross C means projection of A onto this B cross C. So base area times the height, because this is normal. B cross C is normal to this area. So when you are taking the projection of A onto this normal, you are basically getting the height. So height multiplied by area of the base. What does it give you? Can someone answer? What will the result be? Base into height? Area of base into height? What is the result? Can someone unmute and answer? No one? Anyone wants to unmute and answer? What is the result of height into base? Area of base means what? Length into breadth. So length into breadth into height. What do we get? Come on. Length into breadth into height. Class 8 students will be able to tell me. Can you hear me? Are you with me in the class? Anyway, since no one is responding, can you hear me? Can you hear me in the class?
Volume, ma'am.
Yes, volume. What took you so long? Area of the base into height will give you the volume. So the scalar triple product gives the volume of the parallelepiped defined by the vectors A, B and C. Okay. So this is what we get when we take the scalar triple product of the vectors A, B and C. All right. So when you are asked to find the scalar triple product of three vectors, what you get is the volume of the parallelepiped formed by the three vectors. I hope you can understand why we can get the volume, because B cross C will give you the area of the base and the direction is normal. So when you take the dot product of the third vector with that direction, you are basically taking its projection onto the normal to the base. So you are basically getting the height, and height into area gives you the volume, which is why this is the scalar, because volume is a scalar, and this is the physical interpretation of the scalar triple product of three vectors. Has everybody understand, or does anyone wants me to repeat this? I think this is very simple, and you should understand this if you have done your coordinate geometry in your class 10 and 11 and 12 classes. The other form of triple product is the vector product. Okay, it doesn't have a lot of geometrical significance. You only need to know the formula. It is just A cross B cross C. But you have to remember that since this is a cross product, so you cannot interchange the positions of the vectors. In the scalar product, you could interchange the positions and the result remain the same. In the vector product, you cannot interchange the positions because that will change the value of the product. For example, if you take the unit vector, say x cross y, then we know that x cross x is 0, so the result will be 0. However, if you just change the position of the bracket, the first bracket, then it becomes x cross y. But x cross y is z. So this becomes x cross z, which is minus y and not 0. All right. So x cross y is not same as x cross bracket x cross y. So this is what you have to remember. And this is the difference between the scalar product and the vector product in case of vector triple product. In the scalar case, you can interchange the positions because it is a scalar. In case of vector, you cannot interchange the positions, and this example I have shown you proves at once what I'm trying to say. Okay, both have the same vectors x, x and y, but just the position of the bracket changes the result. In first case it is 0, but in the second case it is minus y. All right, so that more or less covers the forms of vector multiplication that you need to do. Now you have to do a little bit of problems, because from vectors you are bound to get numericals in your exam. So in today's class I will just revise 3 or 4 very simple problems with you from what we have done till now, and then in the next class I will start with vector differentiation. Okay, and in the meantime, if it is possible for me, if I get some time, I will also send you a homework assignment. So some sample numericals. First one, find a unit vector which is parallel to the resultant of the vectors that are given, A equal to 2i cap plus 4j cap minus 5k cap, and B equal to I cap plus 2j cap plus 3k cap. So how do you get the solution of this problem? Very simple. I think most of you can do this problem by yourself. So the resultant of A and B, it is given in the component form. So if you remember, then you just need to add the coefficients of I, J and K. So the resultant of A and B is 2 plus 1 3i cap, 4 plus 2 6j cap, and minus 5 plus 3, that is minus 2k cap. So how will you get the unit vector along this direction? The problem asks you to find the unit vector parallel to the resultant of the vectors. So first you find the resultant and then you find the unit vector. So unit vector is nothing but the vector divided by the modulus of the vector. So this is how you get it. Okay, modulus is a square plus b square plus c square root. So this is the result. Very simple problem. Okay. Next problem. Given 4 vectors. This is a simple problem but very important. Okay. So 4 vectors are given, R1, R2, R3 and R4. Now the problem asks you to find scalars A, B and C such that R4 is equal to AR1 plus BR2 plus CR3. So basically this problem asks you to find whether this set of vectors R1, R2, R3 and R4 are linearly dependent or independent. So if you can find scalars A, B and C and write R4 in terms of R1, R2 and R3, it means that these vectors are linearly dependent. But if you cannot find A, B and C, it means that these vectors are linearly independent. Okay, you cannot write a linear combination. So how do you do this problem? See, it is already given R4. You have to write R4 in this form. So let us write R4 in this form. R4 is 3i cap plus 2j cap plus 5k cap, and then I write R1, R2 and R3 multiplied by A, B and C. Okay, so I write this in terms of the expressions of R1, R2, R3 and R4 given. Next, what I do is I gather the coefficients of I cap, J cap and K cap. All right. So if you take I cap outside, then you are left with 2A plus B minus 2C. If you take J cap, then you are left with minus A plus 3B plus C. And if you take K cap, then you are left with A minus 2B minus 3C. All right. So what we have done, we have gathered the coefficients of I, J and K. So next what we'll do, we will equate the coefficients of I, J and K from both sides of this equation. So basically this comes out to be 3i plus 2j plus 5k equal to I cap into this plus j cap into this plus k cap into this, which is possible only if we equate the coefficients of the unit vectors from both sides, right? So we get three equations: 2a plus b minus 2c equal to 3, coefficient of I cap, minus a plus 3b plus c equal to 2, coefficient of j cap, and a minus 2b minus 3c equal to 5, coefficient of k cap. So you have three unknowns, a, b, and c, and you have three equations. What do? You solve the equations simultaneously. And if you do solve it, you can do this, work it out by yourself at home, and the result that you will get by solving the three equations simultaneously is this: a equal to minus 2, b equal to 1, and c equal to minus 3. So what will you, so since we have found values of a, b, and c, so now we can write, now you can write R4 as the bottom portion is not coming, I'm sorry. So you can write R4 as a combination of R1, R2, and R3. Minus 2R1 plus R2 minus 3R3. So this means that this set of the four vectors R1, R2, R3, and R4 are linearly dependent on each other, since they can be written as a linear combination of one another. So this makes my discussion on linear dependence and independence relevant. This problem makes that discussion relevant. So from this problem, you can clearly understand what linear dependence and independence means. Okay, this is a simple problem, but the concept is very important. Okay, next let's see. Okay, this is again a very simple problem, but very, very important, and it often comes in your 2 marks section. You have a 2 marks objective section, so this kind of problem is very common there. So you are given two vectors a and b, and you have been asked to find the angle between the two vectors. So what will you do? You take the dot product of the two vectors. Dot product is, as you remember, sum of the products of the individual components. So a dot b is 2 into 4 plus 2 into minus 2 plus minus 1 into minus 2. So you get 12 minus 6 minus 2, that is 4. This is from the component definition. Remember, I told you that when you are given dot product problems, you have to use both the formulae. So from the component formulae, you get a dot b as 4, whereas from this formula ab cos theta, you get the value, magnitude of a is 9, root 9, magnitude of b is root 49 into cos theta, so 21 cos theta. All right. So from one formula you get a dot b as 4, from the other formula you get a dot b as 21 cos theta, which means that you can equate the two. So 21 cos theta equal to 4, which means cos theta is 4 by 21. Okay, this means that the value of theta is cos inverse 4 by 21. You can find out from your calculator what this comes out to be. I have not done that. So this is how, so whenever you are given two vectors and asked to find the angle between the two vectors, this is what you will do. Okay, you will find the dot product once. Yes.
Mod of b equals to root over 24, ma'am.
What? Mod of b?
Root over 24.
4 4s are 16 plus 2 2s are 4. So 16 plus 4 is 16 plus 4 is 20. Oh yes, yes. Sorry. It will be root over 24. Then probably I have written, I have typed b wrong. Okay. Yeah. Okay. Yeah. Sorry. According to this b, this will be root over 24. Correct. So please correct that mistake. I have probably copied B wrong from my book. Okay, so anyway, this is the method. You find out the dot product from the component form, and then you find out the dot product from the this cos theta form, and then you equate the two and get the result. All right, and please correct this. This will be root over 24. So answer will be 3 root 24. So this will be 4 by 3 root 24. This is, I don't have, this is not a blackboard. This is a prepared slide, so I cannot correct my mistake here. I will correct it when I upload it, but please correct the mistake. Okay.
The half angle theta equals to madam cos inverse 2 by 2 root over 6, 3 root over 6.
Yes, yes, of course. If this is, if this value changes, then the answer will change, of course. If this value changes, then the answer will change. I, most probably, I have made a mistake in copying the vector. Just a second. Just give me a second. Yes, this vector B is not 4 cap, this is 6 cap. Okay. Yes, I have copied this vector B wrong. This is 6 cap minus 3 j cap plus 2 k cap. Okay, I have copied this vector wrong, which is why this answer is not coming. This vector B will be 6 cap minus 3 j cap plus 2 k cap. All right, you all can write down in your copy 6 cap plus 6 cap minus 3 j cap plus 2 k cap. Then the answer is root 49. If the vector is 6 cap minus 3 j cap plus 2 k cap, then this comes out to be root 49. But if this is the vector, then it will be root 24, and then the result will change. But the method will of course remain the same. So if you are given two vectors and asked to find the angle between them, then this is the method that you will follow. Okay. All right.
Okay.
Another kind of problem is find the projection of one vector on another. So you are given two vectors. They have asked you to find the projection of A on B. Okay. So this is again a very simple problem. You just need to know the method. What will you do? You will take the dot product, but dot product of A with unit vector along B, not with B as it is. Okay, since you are asked to take the projection of A on B, so you need to take the dot product of A with the direction of B. So you need to take the unit vector. This is the only thing that you need to remember in this sum. If you are asked to take the projection of one vector on another, then you take the vector and dot it with the unit vector along the other vector that is given. So A dot B cap. So you keep A as it is and you take the unit vector along B, and the result is 19 by 9, which is the answer projection. Okay. So this is the unit vector along B, and then you take the dot product 4 plus 6 plus 7, which is 19 by root 81 is 9. Again, very simple problem, but very important problem. Okay. Last one. This is again very important conceptually. Find a vector which is perpendicular to both I cap minus 3 j cap plus 2 k cap and 5 I cap minus j cap minus 4 k cap. So you are given two vectors and you have been asked to find a vector which is perpendicular to both. So what will you do? How do you get a vector which is perpendicular to two given vectors? Anyone? How will you get a vector?
Dot product.
Not dot
Is equal
product.
to
Dot product gives
product.
you a scalar. Cross product, right? Dot product, result of dot product is a scalar. Here you have been asked to find a vector. So you simply take the cross product.
cross
Okay?
product.
So required vector is cross of the two vectors, which of course you need to calculate I, j, k and this. And please check the calculation. I did it at the last moment in a hurry. I think it is correct. So this is the result. Okay, you just need to take the cross product of the two vectors and that will be perpendicular to both the given vectors. Okay, so these are some simple, very short problems, typically only 2 marks, but all of them are important. So I'll stop recording.